Let's get going. Okay, so today we want to continue to talk about this paper from McCartan, Humphreys, and Alan Jacobs, and some of the commentary on it when it was presented at Columbia. As usual, I, an employee of Columbia, Columbia's experience developed Stan, also use Stan outside of Columbia. That creates the appearance of conflict of interest for me. However, McCartan, although he's also an employee of Columbia, not covered by conflict of interest investigations. Okay, so some examples from this paper that we were talking about on Tuesday, combining what colloquially could be referred to as quantitative and qualitative information. However, the main point of this paper by McCartan and Humphreys on mixing methods is that Bayes' rule, for the conditional probability distribution for what you don't know given what you do know, didn't specify or other restrict the form of what you do know, the data. So it can just as easily be a large number of observations on variables that are relatively cheap to collect, or more commonly already have been collected by somebody else at whatever cost and made easily available to you, versus data that you personally have to invest a lot of time or effort or otherwise resources in order to collect, and thus it's not always feasible for the researcher to be able to collect these supplementary variables, perhaps many supplementary variables of the kind that can be obtained by doing extensive field research for all of the observations. And so the idea suggested in the Humphreys and Jacobs paper is, well, you could just take a subsample of the observations that you have low-cost data on, and in that subsample look for clues, which are additional variables that have different conditional probabilities depending on the type of the observation that you're studying, that has some bearing on what is the type of the observation. And we can combine this analysis, or these two basically blocks of data, those where we've searched for clues and either found them or not found them, or the other block of data, observations where we have not searched for clues at all. One thing that I think is not explicit enough in the paper is that it assumes if you expend enough of your life looking for the clue, you can determine with certainty whether it is present or absent. There's no, at least in the published version, no extension of the model, although they have a number of extensions of the model that they suggest, but don't seem to have a suggestion of the model where you could look for the clue, but the fact that you don't find it doesn't mean it wasn't there. It may have just been classified information or otherwise difficult for you to find if k equals 1 or k equals 0. So that might be an extension to think about, but before we can do anything like that, I want to be clear on the examples that are given in Humphreys and Jacobs and how that fits into the framework for analysis, making causal claims in the absence of an experiment that they put forward. So the first example that they give, which I believe was only in the presentation rather than in the article, do swamps cause death in African countries or other poorer countries. And you might say, well, swamps don't cause death unless people are like drowning in them somehow. The relationship between swamps and death is actually, well, mosquitoes live and are born in swamps. Mosquitoes carry malaria and other sorts of deadly, a lot of times, diseases, and then they bite people. So it might seem a little bit weird to you from a statistical perspective to say, or from a probability perspective or philosophy of science perspective, do swamps cause death? But that's really just a shorthand for like if there was some program that drained swamps, would that increase the life expectancy of the people who live in the nearby area? So it's really what's the causal effect of a proposed intervention rather than a causal intervention on a variable rather than what is the causal effect of a variable. And you can imagine the case that if these swamps have mosquitoes and those mosquitoes have malaria, then a policy intervention to drain swamps would be one thing that you might consider in order to increase life expectancy or otherwise prevent deaths from malaria. But from the perspective of like maybe a ordinary person or the perspective of the so-called qualitative, which I would say is more or less synonymous with process tracing approach to these sorts of things, or at least that's the phrase that's used in political science. I don't know about elsewhere as much, but they do the same sort of thing. I think would take the perspective, well, it's not the swamps cause death, it's malaria that causes death. And mosquitoes cause malaria, and in a manner of speaking, swamps cause mosquitoes to be born. But really the proximate cause of death is malaria. And the proximate cause of malaria is mosquitoes and whatnot. So if you were to investigate whether swamps cause death, you would want to also, as much as you could, collect data on whether or not mosquitoes were present. So if, for example, you had an observation, like a village or whatever with a lot of swamps nearby, and people were dying left and right, but there were no mosquitoes, or not many mosquitoes, or you didn't see that many mosquitoes when you went and looked at it, that would reduce the probability that your theory, hypothesis, etc. is true, that swamps cause death, and would probably lessen your enthusiasm for spending a lot of some foundation's money to just roam all over the place draining swamps, if that's not really the mechanism going on here. But you would need the clue data on the mosquitoes in addition to the data on the presence or absence of swamps and the death rate or the life expectancy or something of the adjacent area. So that is one fairly simple example, I guess, from public health. Within the realm of political science, more squarely, which is where this article is directed toward, many scholars in comparative politics, chief among them, I guess, Charles Bach, have theorized that the presence of strong opposition parties, particularly when combined with the fracturing of existing ruling or governing parties, causes countries to be more likely to switch from whatever system of government they have to a proportional representation system of government where essentially you vote for a party, and then the proportion of votes that each party gets is related to a greater or lesser extent to the number of seats that that party is given in the parliament. And then typically speaking, the parliament, if there's like a majority or they may have to do a coalition, and then they come up with a prime minister out of that, and then things go forward from there. You know, classic examples of this are the Scandinavian countries, Israel, etc. Anyway, so the original study here did a somewhat large-ish and regression analysis of, you know, something relating to the strength of the left parties on, you know, does the country or did the country not switch to a proportion representation system of government sometime in the 1900s. And then a more qualitative study by Kreutzer came along, I guess, much later, and sought several clues that were thought to be relevant if the proposed theory was correct. So did the switch to proportional representation coincide with the expansion of the number of people eligible to vote? That would be a relevant consideration if, you know, you as sort of the existing governing party or maybe king or whatever, and then we're at the same time having like amendments to your constitution or laws that would allow more people to vote. Those more people tended to be women in the early part of the 1900s, etc. You might think, okay, well, if I do this and we have sort of an all or nothing system, and then we have all these people voting who weren't voting before, they are not likely to vote for me, in which case I'm going to get, you know, when the election happens, shut out of the government completely, which didn't always end well for the person or party previously in government. And so you might say, okay. What we need is a proportional system, in which case I might not be in the majority anymore, but I should still have like enough support to possibly, you know, be part of a coalition or something like that. And so if all these changes coincide with the expansion in number of people vote, that would be more favorable to this theory. Even more so, was it the governing party who proposed, okay, let's go proportional representation, or was that more being pushed by the opposition parties? If the opposition parties were doing it, that would seem to be at odds with or for some other reason than what is contemplated by this theory. And then maybe a lesser clue, was there sort of united support among ruling parties or whatever in favor of the switch to proportional representation? If not, that would also kind of cut against there. And so that analysis was done on, I guess, all the original cases and found sort of mixed support for the theory, which originally was found strong support. And now we have the question, okay, we have this sort of large-ish and regression analysis. We have a process tracing qualitative historical approach that, no, I don't know exactly how they determined whether the clues were satisfied. Would probably involve like digging through a lot of old newspaper articles at the time and stuff like that to establish whether K is 1 or K is 0 in these particular cases, and came up with a lot more qualified or not, less support for the theory than perhaps was originally suggested. based on the signs and significant status of the coefficients of the original regression analysis. And so the discipline ostensibly is left with this quandary, how to combine the sort of fairly supportive evidence from regression with the not so much supportive evidence from this process tracing, clue seeking approach. And the Bayesian method, where you just have like two pieces to the likelihood, basically gives you that synthesis of evidence for you. And so that is one of the things that Stan is good at. It makes it relatively easy to incorporate multiple outcome variables or multiple sources of data or multiple contributions to the likelihood function of the parameters, whereas a lot of the packages and other software that you can get out there for frequentist analysis, which wouldn't make a whole lot of sense in this case anyway, but let's say it did, a lot of those packages are geared exclusively toward the case where you just have like one outcome variable and it's all like the same, you just have multiple observations on it. So when you're able to express the numerator of Bayes' rule in a programming language like Stan, you can kind of do whatever you want, as opposed to being restricted in your analyses by the availability of other software and the difficulty of maximizing a function that has contributions from like all different variables. You can easily get multimodality, which is more of a fundamental problem for any analysis that uses optimization than any analysis that uses MCMC and thus is trying to just sample from the entire parameter space with the appropriate probability. So questions about this example on the rise of proportional representation systems? Yes?
Must the clue always be like a hypothesized mechanism to which like X leads to Y? Or can it be like incremental variables?
Yeah, so there's no restriction that like K is a cause of Y or anything like that. It just has to have some association with the type of the observation that gives you more leverage as to whether the country is like type A, type B, type C. So it doesn't have to be like on a particular causal path or anything. It just has to provide more information than what is available from X and Y alone. That's, I think, challenge of these things is finding appropriate clues in an efficient fashion. Third example, also from the paper, is economists, World Bank, Collier, and Huffler, and a number of other studies that come out of the World Bank have asked questions such as, do natural resources cause civil wars, or the presence of natural resources, by which we're mostly talking oil, diamonds, other things like that. There's been back and forth debate about this. Economists are definitely tending to prefer the regression, whether that's instrumental variables or whatever, sorts of studies. Someone named Ross did a more qualitative reanalysis of the original Collier and Huffler paper, maybe an earlier one or something like that, searching for clues and asking the case, well, in these situations where there was like civil wars or not, was there looting as part of the conflict? Where did the rebels get their money from? Was it from selling diamonds? Was it from, multinational corporations who were investing money in their, guns and tanks and stuff, because they anticipated that if the revolution was successful, they would be able to get in there and like drill for oil or mine diamonds or something like that. And so did it seem that there was like financial incentives, financial backing that was related to conflicts such as these? That's another thing that would be consistent with the theory that the presence of concentrated, should perhaps put concentrated, because natural resources is really a continuous sort of variable, but they sort of dichotomize it into like having a lot of natural resources in a small area versus not. So does everybody sort of understand the three types of variables that we're talking about in situations like this? And as we saw from last time, and also in the paper, also in the presentation, that so for the four combinations of x and y, x0, y0, x0, y1, x1, y0, x1, y1, etc., we can obtain the conditional probability of observing that xy pair as a function of some of the elements of lambda, which is a simplex vector of size 4 that contains the proportion of types of countries in the population, which is basically, say, in the world at a particular time, and the pi parameters, which is the probability of being of observing x equal 1 if you're of a particular type and whatnot. And it's a little bit more complicated, but we can still do it for the 8 possible cases of a binary x, a binary y, and a binary k, to also work out the probability of observing that as a function of lambda, pi, and phi. So the probability of basically the clue probabilities that go into that. And there were expressions, we'll see functions of that in the standard code in a second. So very important figure from the Humphreys and Jacobs paper. On the horizontal axis here, we have phi d. So that is the probability of observing the clue, given that the country is of type D. And on the vertical axis here, we have phi b, the probability of observing the clue, given that the country is of type B. And you could do this for type A and type C and all the others. This is just an example. So along the reference line here, which might be a little bit difficult to see, the probability of observing the clue, given that the country is of type D, is the same as the probability of observing the clue, given that the country is of type B. And in that situation, when you're along this line, the clues are, irrespective of what the data on the clues are, they don't help you, because really the function of having clue data is to get, better estimates and whatnot of these probability that a country is of a particular type. And, if you're anywhere along the line, then that suggests the probability that your country is of type D is the same as the probability the country is type B. So that doesn't help you distinguish between those two. In contrast, in the top left and bottom right corners, we have what is known in the process tracing literature as a doubly decisive test. Now, when they use the word test, they definitely don't mean hypothesis test in the sense of looking whether, Z statistic is greater than 1.96 or whatever. What they mean is that if you observe that K is equal to 1, then if you're, up here, okay, the probability of observing K given that you're type B is very high, but the probability of observing K given that you're type D is very low. And so we go out and observe K equal 1, that is strong-ish evidence, depending on exactly how far up into this left corner you are, that the observation is of type B. Conversely, if we go look for the clue and find that K is 0, then that is strong evidence that the country is of type D, destined to have y equal 1, and not type B. And then, the same can be in the bottom right corner here, just the other way around. And so the doubly decisive tests are thought to be like the gold standard or whatever in qualitative research, because you get a lot of information about the type of the observation from just looking for whether K equal 1 or K equal 0. Not in the extreme corners, but more like a little bit off the line. We have some weaker tests. So, hoop test. Well, the probability of, K being present, if you're, up in this region, is bigger, but not that much bigger, suggesting, the probability that countries of type B than type D. And so the fact that you observe K equal 1 doesn't tell you a whole lot. Maybe a little bit, but not a whole lot. Whereas if K is equal to 0, then this becomes a smoking gun test for D. And the same, but reflected across the line in these other places. And then when you're around 0.5, it's a so-called straw in the wind test, where maybe you get like a tiny bit of information, but not only are you really close to the line, you're really close to the line around 0.5. So not really getting a whole lot of information about the types in your data. And like I said, you can do this for type A, type C, all of those. And thus, basically, where you fall in this square is an indication of how successful your clues are, or how successful your research design is in terms of leveraging the information that could be obtained on the parameters that you're seeking. This is originally intended for sort of a purely qualitative analysis, but Humphreys and Jacobs, because they're looking at things probabilistically in a Bayesian framework, is easily able to incorporate it into the procedure that they're suggesting. So questions about this sort of classification of tests, not that you have to remember like what's the difference between a hoop test and a smoking gun test and a doubly decisive test, but this general idea, because like really we're talking about a continuous square here of, depending on where you fall in that square, providing more or less evidence that an observation is of this or that type, depending on whether K equal 1 or K equals 0. And basically, the more you are toward the corners, the better it is for your research prospects Because if either k equal 1 or k equals 0, you're learning something, or you're learning a lot. Whereas if you're in one of these more intermediate areas, you might be learning more from k equal 1 than if k equals 0, or you might not be learning very much at all. Questions about that? Okay. So if we were going to do this in Stan code, which the authors of the paper actually did, but this was a few years ago before we started harping as much on the importance of doing simulation-based calibration. So we talked about this last Thursday, but we were sort of running out of time. So I don't know if it was completely clear. The idea of simulation-based calibration is something you can do before you even collect the data on the outcomes or the clues or whatever. And the premise of it is, if you draw from your priors distribution and you use the realizations of the draws from those prior distributions to draw from the conditional distribution of the data given the priors, which is to say to draw from the prior predicted distribution, and then you take those realizations of draws from the prior predicted distribution and condition on them in order to obtain a posterior distribution, then mathematically speaking, your prior distribution cannot be systematically different from your posterior distribution if you're conditioning on data that was drawn from the prior predicted distribution. And that can be proven as sort of a basic mathematical fact. But if you have evidence to the contrary, then that suggests that you have a bug in your code, which is what happened last week when I was trying to show instrumental variables, or there's a limitation of your software such that it's not able to draw correctly or efficiently from this posterior distribution. And so just because you can write down the numerator of Bayes' rule does not mean it's going to necessarily be possible for Stan to draw from that posterior distribution correctly. Now, this semester we've overwhelmingly seen examples where Stan can do just fine. Maybe you have to increase a depth delta or something like that in order to get warnings about divergent transitions to go away. But we haven't seen any situations in which Stan just failed. And those seem to be on the rare side, which is good, but even more important, in any particular situation, you can make an assessment as to whether Stan is going to be able to do well or poorly in drawing from the posterior distribution by you repeatedly drawing from the prior, repeatedly drawing from the prior predicted distribution, taking your realizations of draws from the prior predicted distribution, conditioning on them, obtaining a posterior distribution, and sort of systematically comparing it to the realizations you got from the priors. And if there's sort of no systematic differences, then you can be fairly confident that Stan is going to be able to work correctly with your exogenous knowns, with your priors in the exact situation that you want to do. Okay, Stan looks like it's going to be pretty good, or here are some things to watch out for if, you know, when you do this, you get like a lot of divergent transitions or something like that. Moreover, if you go through all these steps and you find, okay, I think Stan is going to be able to do this pretty well, and then you collect data from the wild and you find, you know, all kinds of warnings about divergent transitions that didn't converge, all kinds of other things that said Stan didn't do a good job of drawing from the posterior distribution in that case. Well, now you know or have strong reason to think that the data that you collected wasn't generated by the model you envisioned when you were drawing from the prior predicted distribution, because you'd already established Stan works fine by doing a bunch of simulations there. And so if you see Stan not working fine on actual data, then it's presumably the case the actual data was not generated by the model that you specified. And that's also really important information and data. So one of the very important things about Stan is that it oftentimes works well, but when it doesn't work well, it's apparent, and it's apparent in ways that sort of suggest to you what sort of modifications need to be made. So we want to do an example from the sort of base model in the Humphreys and Jacobs paper is how we would do simulation-based calibration. And so we start by defining in the functions block of our Stan program the two functions that calculate basically the simplex vector that we're going to need to evaluate the multinomial likelihood in the Humphreys and Jacobs paper, which is the log likelihood is going to consist of the sum of two multinomials. So we're going to need two simplex vectors, each of which are a function of the lambdas and the pi in the first case, and the lambda, the pi, and the phis, the probability of observing the clue in the second case. And so these expressions are the same ones that we saw on Tuesday. So for example, the probability of observing x equals 0, y equals 0 in an observation where you don't look for the clues is the lambda 2, the marginal probability of being type B, times 1 minus pi 2, which is the probability of observing x equals 0, given that you're type B, plus this other one, lambda 3, times 1 minus pi 3 for the probability that x is 0, given that you're of type C or whatever it may be. So you can do those for the 4 possibilities when you don't search for clues. When you do have observations where clues have been sought and K has been observed, now there's 2 to the 3 possibilities, and so there's more terms here in order to fill out the 8 elements of this simplex that you need. I used a convention that I basically just made up, where if I use all capital letters, that's 1 minus that probability, and then I can multiply and add stuff in order to get out the probabilities I need to evaluate my likelihood function of lambda pi and phi 0 and phi 1. So that's all those functions do, implementing the equations that we talked about on Tuesday. And so we'll need to call those two functions as we go along. Questions about this? It's just the Stan version of on Tuesday. Okay. So then what are the data and transform data blocks? So in the data block, when I'm doing simulation-based calibration, I only want to pass in the exogenous knowns, not the endogenous knowns, because I'm going to generate the endogenous knowns in the transformed data before I actually collect data on them. So you might think of it as your endogenous knowns are not known yet, or you're pretending like you're not knowing them yet because you don't want to condition on them yet. So the exogenous knowns in this case are simply the number of observations where you have X and Y data only, and the number of observations where you have X, Y, and clue data. So those are mutually exclusive, even though they talk about in the paper, well, you collect like a bunch of observations and then a subsample of those you go look for clues. The other exogenous knowns are the things that go into our priors, AVEC, which is the Dirichlet shape parameters that go into the prior on lambda, A pi and B pi, which are the shape parameters of beta priors on the pi. Values the probability of observing X, given that you're of this or that type. Also, we have shape parameters for A, phi, 0, B50A51 and B51, the probability of the shape parameters for the probability of observing the clue, given that you're of this or that type, and whatnot. So those all go into our priors, and then in the transform data block, we're using that when we're doing simulation-based calibration to draw from the priors, draw from the prior predictive distribution, and then condition on that data that we drew from the prior predictive distribution to get the posterior, and then check whether that is systematically different from the realizations we obtained from our prior. So this is only going to happen once per time that we call stand, so we're going to have to call stand repeatedly, but there's a function now that facilitates doing that. So we first draw a realization of the simplex, which I call lambda underscore. So again, a convention that I basically invent is to postfix underscores onto things that are realizations from the prior. So I draw that from a Dirichlet distribution with shape parameters AVEC that I declared in the data block, and now I have a realization of these four numbers that are non-negative and add up to 1 for lambda. Then similarly, I declare, because I'm going to have to fill them in later, realizations for pi, for phi0, and for phi1, and realizations for the data of which there are in xy of so this is going to have 4 elements to it, and this one for x, y, and k is going to have 8 elements to it. And then I go to fill those in. So first, I loop over the 4 types of observations and draw pi, phi0, phi1, the 4 elements of those from the respective beta distributions that represent my priors on the clue probabilities in the case of phi, and also the probability that x equal 1 given your type, or x equals 0, x equal 1, it's just 1 minus one of the other, given your types as well. And then now I have realizations of all my parameters. I'm set to draw endogenous knowns from their prior predictive distribution, which in this case is a multinomial. And so I draw from a multinomial, calling my wxy function, which I have declared in the function block, to produce that simplex, depending on my realization of lambda underscore and pi underscore and the number of such observations that I want. And then similarly take a draw from a multinomial distribution, but now calling the other function that I declared in the functions block to give me that simplex of conditional probabilities and then the number of observations that I want, where we have x data, y data, and clue data. And so here, basically what I've accomplished in my transform data block when I'm doing simulation-based calibration is to get these realizations from the prior predictive distribution of the endogenous knowns. And then Stan is going to treat those as just regular endogenous knowns in the rest of my Stan program, so we can get a posterior distribution conditional on these things. Questions about that? Okay. So the parameter and the model block are actually fairly simple, I would say, in this case. We have, sort of true parameters, lambda, pi, phi0, phi1. These differ from the ones that I declared in the transform data due to the lack of trailing underscores. So with Stan, all your symbols have to be unique. So we need some way of distinguishing these realizations from the prior from realizations from the posterior distribution conditional on the data we drew from the prior predictive distribution. So these are my parameters: lambda, the share types, pi, phi0, phi1, probability of observing the clues. And then we go into the model block where we just need to specify the numerator of Bayes' rule that corresponds to our generative models, always remembering we need to express these densities and probabilities and likelihoods and whatnot in log units. So our prior for lambda was Dirichlet, but it's now Dirichlet LPDF for the log PDF, conditional on the shape parameters we passed in data. Log beta PDFs for pi, phi0, and phi1, conditional on the stuff that represented our prior beliefs going in. And then the likelihood contributions, multinomial LPMF, because the XY and the XYK data are integer valued. So the logarithm of the likelihood is represented by multinomial LPMF for these, given the simplex is the result from evaluating the two functions we defined in the functions block when passed in a proposal of draws from the posterior distribution. And so up here, we have the contributions to the numerator of Bayes' rule in log units that come from the priors on the parameters. And then here we have the contribution to the numerator of Bayes' rule coming from the log likelihood. And given that information, that numerator of Bayes' rule, Stan can then sample from the posterior distribution of these parameters conditional on the data. But the data in this case was just draws from the prior predicted distribution. So once Stan is done drawing from the posterior, we can assess how similar or different or systematically different these draws from the posterior distribution are from these realizations from the prior distribution we obtained in transform data. And if there are any systematic differences, then we know either there's a bug in our code or Stan is not working well for a posterior distribution defined in this way. Questions? So all this comparison stuff can be implemented using the generated quantities block, which we haven't talked about as much, but it can be used to store realizations of things that aren't needed for like the log likelihood, but are of interest for various reasons. So one of which is the average treatment effect. And so that is defined in the paper as lambda b minus lambda a, the proportion of observations who are beneficially affected by treatment minus the proportion of observations that are adversely affected by treatment. And so this is sort of a net effect of is the treatment good. We want to declare log a lick. So I'm not sure if we've seen this yet, but if you want to do loop after you do calling rstan, then you need in the generated quantities block to define a vector called log underscore lick that contains the log likelihood contributions for each of the observations. In this case, it's observations from the prior predicted distribution. But among the things that you might want to check out is for this data generating process, are we in a situation where like a few observations are extremely influential by evaluating the Pareto K shape statistics? So in order to do that, when you're writing your own STAN programs, you need to put in the generated quantities block these log likelihood contributions for each observation. Whereas with RStanArm and VRMS, it does that for you. But when you're doing stuff on your own, you need to do that yourself. Also, we declare a vector, in this case of size 16, called pars underscore, which I'm going to copy in my realizations from the prior. So I have those in case I need to investigate like what shape do my priors all imply for these parameters. And then finally, I declare an integer array also of size 16 because I have 16 parameters in this particular case, where I just go through and evaluate whether lambda 1, so my realization from the posterior distribution, is greater than lambda underscore 1. lambda underscore 1 being my realization from the prior distribution. And so you might say, okay, you know, lambda 1 should not be systematically more or systematically less than lambda underscore 1 if everything is going well. And the same, I do that for lambda 2, all the lambdas, all the pi's, all the phi zeros, all the phi 1s. And so for each of my parameters, I'm basically evaluating, well, what's the probability that this posterior draw is greater than the prior draw? And if that ends up all lopsided, I know something has gone wrong. And so the rest of this is just, you know, filling in all those vectors and whatnot. And then in these blocks over here, evaluating the categorical likelihood for each observation, or the likelihood contribution from each observation to the parameters. And then if I have that, when I call Lou, or it's called internally, I can evaluate the Pareto K statistics. So when all that you're satisfied is working good, and we'll see how to do that coming up next, then all you have to do when you're ready to actually condition on data that you've collected from the wild is comment out all that stuff from, you know, simulating from the prior and the prior predictive distribution, elevate your exogenous knowns from transform data to data, and then comment out all the stuff you don't need anymore from generated quantities, and you're ready to go. So this helps, you know, to sort out bugs and whatnot in your code. But once you're satisfied that everything's working, all you have to do is comment out some extraneous stuff for SBC that you don't need anymore, and now you have a STAN program that's ready for conditioning on data that you've collected. So you don't have to write like a totally new STAN program, risk introducing more bugs or anything like that. All you have to do is comment out this stuff that you don't need anymore. So how do we do this? Like I said, the next version of RSTAN, which hopefully should be out next week, has this function called sbc.r that you can source in. You call the stan underscore model on your program that I just defined there to compile it to a thing that I call SM for stan model. Then you create a named list of the exogenous knowns that you want to pass in to the data block. So here you should be using, you know, your actual priors and the actual number that you anticipate to have, you know, XY data only versus XY and K data, so that the simulations that you're doing with simulation-based calibration are actually tailored to the analysis that you're planning on doing. I just did some like kind of generic priors with, you know, 1s for all these shapes and 10 each observations for, you know, those without clues, those with clues, but you should customize that to the actual priors that you plan to use, and then call the SBC function, giving it the compiled model of the data, how many times you want to call this whole thing. So I did 2000 here. That argument is called M, whereas I guess in most other times, previous weeks, we would have called that S, the number of simulations you want to do. But actually for each of these 2000 draws from the prior predictive distribution, it's drawing like 1,000 times from the posterior. Anyway, that takes a little while, but actually not that long for a model like this. And you get back a collection of results telling you some stuff about how well this all went. So good news, no chains had any divergent transitions after warm-up with just the default settings. So one of the things that you might find when you do this is there's divergent transitions, in which case you know you might have to bump up adapt delta to like 0.9, 0.95, 0.99, whatever it is, to eliminate all those divergent transitions, hopefully. And so if that happens, you might have to run it again, but you get a sense as to what value of adapt delta you're going to need when you do your actual analysis conditioning on your actual data. But in this case, even with the default settings, no divergent transitions. And when that happens, it's usually going to be the case that Stan is just fine. So that's sort of the number one threat to Stan not working well, is having divergent transitions, indicating there's a part of that posterior distribution that it couldn't get to, given how big of steps it was taking. So that's good. We also get these Pareto K hat statistics by internally calling the Lou function and evaluating all that. And we see that like over 96% of them had Pareto K values less than 0.5, which is very good. Like 3% of them had between 0.5 and 0.7, which is, that's only a small percentage. Fine. Very occasionally, probably nothing to worry about, but there's a small chance that you would have some observations that are a little bit too influential to be happy about that. But that was only a couple times that happened out of like 2,000 by 20, and then no ones that were sort of intractable. In this case, 0 to infinity for the Pareto shape. So overall, this is suggesting there's no obstacle to Stan working well for a posterior distribution like this, but we can gauge this more specifically by looking at a plot of those results. And here, what you're looking for are histograms that are essentially uniform. This is based on those ranks values that we were calculating in the generated quantities block. So what is the probability the posterior realization is higher than the prior realization? That should not systematically be the case. And so, when there's a high prior realization, there's a low probability that the posterior realization is going to be higher than that, and vice versa. But overall, when things are working well, these histograms should look uniform and with these rank normalized statistics, and by and large, they do. However, it does seem to sort of be a systematic trend a little bit, that the last two bins seem to have not as many observations as the rest of them. So you can see that for basically all the parameters. And that would suggest when you have extreme values from the prior distribution, so like when lambda 1 is really close to 0, or lambda 1 is really close to 1, or something like that, which is to say there's almost no or almost all of your observations are of that type, then it looks like Stan, even though there's no divergent transitions or Pareto K or anything like that, it looks as if Stan is missing part of the posterior distribution in that case, because we have some noticeable but minor non-uniformity at the edges. And so that would be a thing to be concerned about if you actually thought it was realistic that there could be like no or all type A, in lambda. Usually if you're doing this, you would have, a more informative prior that, some sense in which all of the 4 types are, prevalent, as opposed to having these extreme situations where it's like all or nothing. So if you use, uniform priors on these Dirichlet's, then that's it. These extreme situations are as likely as everything else. And that's why you want to do this with the real priors. Because, maybe these situations in which Stan is not doing so good, might be missing a piece of the posterior distribution, is something that you don't think is likely to happen in the first place. So I did this with just flat priors everywhere, but you want to do it with the real priors. Anyway, you can always do this. You can always do this before you actually have the data. You can always do this if you're writing up a pre-registration deal that says this is what I'm going to do and this is the code I'm going to do it with. And I know Stan's going to work well, or I know when Stan might be having some problems. And so you want to pre-register all that. And you have a working Stan code from when you want to actually condition on your data. So this simulation-based calibration is a really important step to go through. And it stands, and you might want to have like a Amazon cluster or something to do this, because it can take a little bit of time, or a lot of time actually. But this is one of the areas in which I think a Bayesian, not that many people are doing simulation-based calibration, even though we recommend that they should, but where Bayesian analysis can and should be a lot more rigorous than what passes for being rigorous with a frequentist analysis. And so one of the most common complaints that you'll see people who aren't really that frequentist philosophically, but only use frequentist methods is like, well, the Bayesian methods all take too long. And it's like, complicated to get set up and all these sorts of things. And that is only true if you're sort of allowed in a frequentist estimator to go on and estimate your thing without doing any verification at all of whether the asymptotic results that frequentist estimator assumes when it spits out p-values, confidence intervals, standard errors, etc., are at all applicable for your number of observations and your data generating process. So like if it was the case before you were allowed to publish or pre-register something where you were going to do a frequentist analysis, you had to demonstrate that your estimator that you were planning to use was going to work well with 17 observations. And you had to do all those simulations for all different possibilities that the data could be before you collected it. So if the frequentist had to do all that work, then that wouldn't be like orders of magnitude different than the amount of work you would need to do for Bayesian. So all this stuff, oh, well, frequentist is so much easier, I don't have to do a whole lot of work, is because they're like allowed, for reasons that they made up themselves, to not have to worry about the performance of the estimator in finite samples if there's some assurance that the estimator works well in infinite samples. Okay, yeah, if you can skip that step, then yes. But if you skip that step, you put yourself in a situation in which the conclusions that you reach, or the statistical significance, whatever that you find from these asymptotic formulas for the p-values based on asymptotic normal sampling distribution for the estimator might not be descriptive at all of the sampling distribution that's implied for the amount of data that you have and the data process that you're considering. Again, this idea of like asymptotic in is basically license to not have to worry about the particularities of the parameters in the data generating process. So for sufficiently large n in some models, the sampling distribution is asymptotically normal, irrespective of what the true values are. For finite n, the sampling distribution of the estimator is always going to depend on what the true values of the parameters are. And it's actually a whole lot of work to establish that your estimator is going to work well across the whole range of what the parameters can be when you're talking about finite n. And that's really just a step that a lot of non-Bayesian analysis are skipping. And we don't want to skip that when we do stuff with Stan, because we don't have to. We can have pretty good assurance that Stan is going to work in a particular case if we just do this SBC stuff. So questions about that? Okay. So they have some examples in the Humphreys and Jacobs paper and come up with the following implications for research design. One of which is there's diminishing marginal returns to both types of data. So if all that you have is like X and Y, then getting even one observation where you find the presence or absence of a clue can make a big difference to the accuracy in the precision with which you estimate the treatment effect in yours. But if you like have 3 observations with X and Y and like 1 where you have X, Y, and K, then getting a second observation where you have the clue data isn't as valuable as getting an additional observation where you don't have the clue data. And so it sort of depends on where you are at in that, and that was represented by this figure here. So black means you find clues or get K for all of the observations. White means none of the observations, and gray like 50%. So you can see the expected squared error is sort of decreasing as the logarithm of the number of cases increases. But sort of the dent that you make from going like no observations with clues to all the observations with clues or half the observations with clues isn't as impressive when you're getting more observations. So that's one thing. They can data with and without clues can partially be substitutions for each other. So if you don't have that many with clues, you can partially substitute that with more observations that don't have clues. And then what I think is probably one of the more interesting points is that the optimal research design that you might plan when you're doing your prospectus or whatever, in terms of how many and which countries you should seek the clue data on, that depends on the fees and the lambdas, and therefore depends on your priors on the fees and the lambdas. And so how many of these you get depends on what priors you plan on using in terms of a priori being able to estimate how well you're going to be able to obtain the posterior distribution of the treatment effect. And so one of the limitations, or it's not really a limitation, but critical demand that they recognize is that researchers have to be able to state priors over the causal effects, the assignment process, and the clue probabilities. And that seems particularly difficult or maybe arbitrary for the clue probabilities. But that's just sort of a fundamental aspect of this particular approach. And then a couple pages later, they go on to say, well, this demand for the Bayesian approaches certainly considerable, and it's the reason why I think this paper hasn't been all that influential in political science. But they say they believe it's true because it places high demands on the researcher's belief, because everything is explicit and transparent as to how it goes into the generative model and the posterior distribution and all that. The extent to which scholars are unable to specify priors, even approximately, on all these stuff, especially the clue probabilities, is a problem for causal inference, not for the Bayesian integration of quantitative and qualitative information framework that they're talking about. And the framework helps to identify what sort of research designs you would want to do to sort of maximally give the ability to provide a causal account for these sorts of things. So we started a little bit late, so one more thing to get through. Using the BRMS package to generate stand code. So you don't have to start out writing a blank stand program every time. You can use the make stand code function in the BRMS package to look at or maybe subsequently modify the code that BRM generates. And there's a corresponding make stand data function that's also exposed to generate a named list of R objects to pass to the data block of the stand program that was generated by make stand code. So if you load up BRMS and then call make stand code, make stand data with the formulas and the data and the prior and all that, instead of BRM, this is a list of data and this is a string vector representing the code. And then you can look at those things. So that make data, stand data produces a list, in this case of size 10, saying what N and Y and K and X and the stuff for your priors and Z is. So this is a multi-level model with separate intercepts for each patient that have some sort of epilepsy condition and modeling the count of the number of seizures as a function of their age and their medication. And then you have this sort of person-specific additional shift in the severity of your epilepsy symptoms and priors for everything as well. So you can sort of flip back and forth between the code that BRMS generates for this and the list of data that it made from your data frames and all that. So we have 236 observations, and this is what the first few values of Y like, 3 predictors, et cetera, et cetera. So you can look through that. We won't have time to go through this, but just wanted to call your attention to, if you call make stand code with that example, it spits out a character vector string, looks like this, which is literally the code that BRMS is then translating to C++ and compiling if you were to call BRM on that. But maybe you say, okay, I want to do something that BRMS can't do. Well, start with the closest thing that BRM can do. You have valid transformations or whatever of the data frame to the data you need for the exogenous nodes and endogenous nodes. And then, it's done what you told it, but save that to a stand file and then start making your changes. So you can go through all this. It centers the predictors, it declares the parameters, goes through, makes mu, the priors, that's where all the student T and Cauchy and all that comes in. There was censoring, so that's why you have some of this. And then if you want to evaluate the likelihood, so if this is 1, then it's just drawing from the prior, and that's how it can do some of the same stuff that RSting arm does. But if you want a condition on the data, okay, there's a Poisson log likelihood, piece in there. So that is a good building block for starting to do your own amendments to that stand code. Okay, out of time for today. Pick it up on Tuesday. Start talking about doing some missing data stuff using STAM programs. I will also post tonight the last homework. It will involve writing some STAM yourself, and this is basically why for all those weeks we had to kind of rush through stuff. Didn't always have a lot of time to talk about the answers to the homework during lectures and whatnot, because we had to hit April 25th or whatever it was to be able to make the last homework on doing things yourself in STAN. So it'll be due Thursday, which is like the last official day of this class, and we'll talk about the answers to that then. But on Tuesday, we'll be starting to talk about missing data stuff, so check out the reading for that. Okay, so see you.